Okay, I want you to do a quick mental exercise with me. Picture a supercomputer. I'm talking, state of the art. Blinking lights, cooling fans, humming like a jet engine, the whole deal. It can simulate galaxy formations, calculate pi to 1 billion decimal places.
So the absolute pinnacle of logic.
The absolute pinnacle. Now, type a single sentence into that machine. Sentence that makes perfect sense to you or me, but is specifically designed to just break its brain. Type, we can a can.
Yes. The classic linguistic torture device.
Right. To a human, it's a bit silly, but it's grammatically sound. We get it instantly.
But to a computer, that looks like a glitch in the matrix. It sees the same pattern can over and over, and it just short circuits.
Exactly. It's a chaotic loop. And that specific chaos, that's our jumping off point for today's deep dive. We are exploring the crisis of, well, lexical ambiguity resolution.
Which is really just the fancy academic way of saying, how do we teach a machine to understand that the same word can mean 3 completely different things depending on where it sits in a sentence?
Welcome to the deep dive. Today, we are unpacking part of speech tagging. And I know that sounds like something you might have slept through in 3rd grade grammar class.
It does. Nouns, verbs, adjectives, it sounds elementary.
But here's the hook. Teaching a machine to do this, to look at a text and accurately label every single word with its correct grammatical role, has been one of the single hardest hills to climb in the history of artificial intelligence.
It really has.
So our mission today is to trace that climb. We're going to see how we get from a computer looking at can, and saying total nonsense, to a computer that uses deep learning to, read sentences backwards and forwards just to figure out the meaning.
And we're going to find out why, despite throwing these massive neural networks and supercomputers at the problem, we seem to have hit a very, very human ceiling.
Okay, so let's start at the very, very bottom. Before we can even argue about whether a word is a noun or a verb, the computer has to acknowledge that it is a word in the first place.
Right. This is the foundation layer, tokenization.
Which intuitively feels like the easiest job in the world. You just tell the computer, look for the white spaces.
Yeah.
If there's a space that's the end of one word and the start of another, done.
If only language were that cooperative. The source material points out that white space is actually a terrible indicator of meaning.
How so?
Well, take the city New York.
2 words, 1 space.
On paper, yes. But semantically, it's one token. It's a single entity. If you split it into new as an adjective and York as a noun, you've actually lost the meaning of the city.
Right. You have to teach the machine those 2 pieces stick together.
And then you have the complete opposite problem, which the sources highlight with the Italian word damelo.
Damelo, okay.
1 word, no spaces at all, but it translates to give it to me. Syntactically, that single string of characters is doing the heavy lifting of a verb, a direct object, and an indirect object all at once.
So if you just split by spaces, you're missing all that internal data. You're slicing right through the meaning.
Exactly. So step 1 isn't just cutting up the sentence. It's splitting it into these meaningful chunks or tokens.
Yeah.
But as soon as you've done that, you walk right into the next trap.
The ambiguity class.
It sounds like a sci-fi social hierarchy, doesn't it?
It really does. But in our context, this is the core problem. The source material explains that most common words they're shapeshifters. They don't have a single identity.
Let's go back to your can example. In the machine's dictionary, its lexicon, the word can belongs to an ambiguity class. It lists every possible thing can could be.
Okay.
It could be a modal verb, like I can run. It could be a main verb, like I can fruit. Or it could be a common noun, like pass me the can.
So the machine looks at the token can, and it doesn't see a definition. It sees a multiple choice question, and it has to pick the right answer without having a brain.
Precisely. And this is where we have to give the machine a substitute for a brain. We call it a priori knowledge.
Which is basically what humans have, right? If I say the and just stop talking, your brain is already priming itself for what comes next.
Right. My internal language model just screams, noun. I'm expecting the cat, the house, the idea. I am absolutely not expecting a verb. The run or the eat sounds wrong to me because I have years of data, just life experience, telling me that articles are followed by nouns.
So we need to give the computer that same intuition. And historically, the way we did that was just pure brute force mathematics. We started counting.
This is the era of the statistical approach. specifically the Enneagram model.
I love how simple this actually is when you strip away the jargon. We aren't teaching the computer grammar rules. We're not teaching it definitions. We're just teaching gambling odds.
That's a great way to put it.
Yeah.
We take a massive amount of text that has already been tagged by humans, this is our training corpus, and we feed it to the machine. And the machine just, it starts counting frequency.
It asks two main questions, right?
First, it asks, how often is the word "can" a noun versus a verb? That's the raw frequency. Maybe in the Wall Street Journal corpus, it's a verb 90% of the time. That's your baseline.
But that's not enough. Because in our sentence, we can, a can. The frequencies are all over the place.
Correct. So it asks the second, much more important question, context. Specifically, how likely is this tag given the previous tag?
And this is the Enneagram part, looking at the neighbors.
Yep. If the previous tag was an article, like A, the probability of the next tag being a noun just skyrockets. And the probability of it being a verb, it plummets to near zero.
So mathematically, a can becomes article noun. The math just solves the puzzle for you.
Ideally, yes. You multiply those probabilities together, the probability of the word and the probability of the sequence, and you find the winner. But there's a catch.
There's always a catch.
The problem is that a sentence like "we can a can" only makes sense if you look at the whole sentence structure. If the computer just looks at "we can," it might get it right. But if it looks at can, it might get confused.
So if you use a sliding window, just looking at the immediate neighbor, you can miss the bigger picture.
You're being short-sighted. It's like trying to navigate a maze by only looking at your feet.
Right.
Exactly. To solve this, the statistical models use something called the Viterbi algorithm.
Okay, now, without getting us lost in the calculus, what is Viterbi actually doing?
Think of it like a GPS finding the best route. It doesn't just look at the next turn. It calculates every possible combination of tags for the entire sentence, from start to finish. Then, it prunes away the paths that are mathematically unlikely.
So it finds the path of least resistance?
Or the path of maximum probability. It makes sure that the final sequence of tags is the most logical story the numbers can tell for that whole sentence.
That sounds surprisingly robust. If you have enough data, shouldn't that work perfectly?
It works beautifully, until the computer meets a stranger.
The unknown word.
The jargon for this is OOV, the out-of-vocabulary word. And this brings us to a fundamental law of language called Zipf's law.
This is the idea that, a few words are used constantly and most words are used very rarely.
Exactly. The and, of, you see those millions of times. But no matter how big your training library is, you could feed the machine the entire internet. There will always be words in the long tail that it has never, ever seen before.
New words, slang, typos, brand new proper names.
All of it. So if I type uninstagrammable and the machine has never seen that word, its probability counter just hits zero. And usually when you multiply by zero, the whole equation just crashes.
So the system breaks.
It breaks. It's the data sparseness curse. So we need a backup plan. We need the machine to be able to guess.
And this is one of my favorite insights from the source material. How does a machine guess the meaning of a word it's never seen? It looks at the word's tail.
Suffix analysis. It is surprisingly effective. The source mentions the TNT tagger, which was developed by Thorsten Brantz. It looks at the last few characters of the unknown word.
Because in English, the end of the word often tells you its job.
Take words ending in "able," fashionable, reliable, capable. In the training data, 98% of words ending in "able" are adjectives.
But not all of them.
You've got table, cable. Those are nouns. But if you're a machine and you have to place a bet, 98% is a winning hand. So when it sees uninstagrammable, it sees that abial suffix and bets adjective.
And that simple heuristic actually works.
That specific tagger reached 89% accuracy on words it had never seen before, purely by analyzing suffixes and capitalization.
Wow. That's much higher than I would have guessed. It's like the machine is learning the shape of the language, not just the vocabulary list.
And to keep the math from crashing on that 2% error, we use something called smoothing. It's a technique like Nézerné smoothing, where we basically steal a tiny bit of probability from the words we do know and sprinkle it over the words we don't.
So zero probability never actually happens.
Never. The machine is always allowed to think, well, it's remotely possible.
Okay, so we've got tokens, we've got probability counting, and we've got suffix guessing. This brings us to a fork in the road in the history of this technology, the battle between generative and discriminative models.
This is a really crucial distinction for anyone interested in how machine learning actually thinks.
So the classic statistical approach we just talked about, the Viterbi stuff, that's usually a hidden Markov model, or HMM. That's generative.
Right. And HMM assumes there's a hidden cause generating a visible effect.
Like a doctor.
Exactly like a doctor. The disease is hidden inside the body. The symptoms are visible on the outside. The doctor looks at the symptoms to guess the disease.
So in our case, the tag, non-verb, is the hidden disease, and the word is the visible symptom.
Precisely. The model tries to reverse engineer the hidden sequence that generated the words. It's elegant, but it's a bit rigid. It relies so heavily on those strict word-to-tag probabilities.
And that rigidity is why the field shifted over to discriminative models, things like maximum entropy or maxent.
Maximum entropy sounds like a chaotic physics theory, but in AI, it's actually about freedom. It lets us stop just counting words and start using features.
And features just means clues.
Yes, clues. And HMM is pretty much limited to what is this word and what was the last tag. A maxent model lets you program in any clue you think is relevant.
The source lists some really specific examples of this.
It does. You can tell the model, hey, if the word ends in ing, I want you to boost the probability that it's a verb. Or more complex ones, like if the current word is about, and the previous two tags were a determiner and a plural noun, then about is probably a preposition.
So instead of just blindly counting, you're giving the machine a detective kit.
You are. You're giving it logical rules to apply alongside the math. It discriminates between options based on a much richer set of features. But Maxent had its own flaw, something called label bias. It was still making decisions step by step. It sometimes got tunnel vision.
Which leads us to the conditional random field, or CRF.
Think of a CRS as Maxent, with a bird's eye view. It takes all those rich features, capitalization, suffixes, neighbors, but it solves for the entire sentence at once, just like the Viterbi did. It combines the flexibility of features with the global logic of the whole sequence.
And for a long time, CRFs were the kings. If you were doing text processing in the 2000s, you were using a CRF.
You were. But then, the revolution happened.
Deep learning. The neural networks entered the chat.
And they brought with them an acronym that sounds like a secret government weapon.
The BILSTM CRF.
It's a mouthful. But if you take it apart, it's actually a beautiful piece of engineering. It represents the modern way machines read.
Okay, let's dismantle it. We start with the RNN, the recursive neural network.
The key difference here is memory. The old statistical models were largely looking at these fixed windows. And RNN has a loop. As it reads a sentence, it carries information from the beginning of the sentence forward to the end. It remembers what it just read.
But the source says the real magic letter in that acronym is the B.
The B for bidirectional. This is the game changer.
How so?
Imagine reading a sentence, but you can't see the end of it. You're uncovering one word at a time. The man who?
The man who runs. Okay, runs is a verb. Easy.
Easy. But what about the runs?
Could be the runs in her stocking, which is a noun, or the runs scored in the game, also a noun. I need to know what comes next to be sure.
Exactly. Context doesn't just flow from past to future. It flows from future to past. To understand a word, you often need to know what comes after it.
So a bidirectional RNN reads the sentence left to right, A and D, right to left at the same time.
Simultaneously. It essentially travels through time in both directions, combining the past context and the future context to make a decision on the current tag. It creates a complete 360-degree view of the word's environment.
That is wild. It's like the machine is omniscient, but only for that specific sentence.
Then you add the LSTM long short-term memory. This fixes the goldfish memory problem of basic neural nets. It lets the machine remember a dependency from the very start of a long paragraph that affects a word at the very end.
And then finally, you slap that old reliable CRF layer on top to make sure the final output follows the rules of logic.
And the result. This Frankenstein monster of a model achieves 97.55% accuracy on the Wall Street Journal test set.
97.55%. That is incredibly impressive. It feels like we've solved it.
You would think so. But the deep dive takes a twist here. Because despite these massive neural networks that require huge computing power, the source material talks about a comeback.
The return of the rule-based system.
Yes, the revenge of the linguists.
Yeah.
For years, the data scientists said, don't write rules, just let the data speak. But now we're looking back at systems like constraint grammar.
Constraint grammar is fascinating because it works backwards. It's reductionist.
It's the Sherlock Holmes method.
When you have eliminated the impossible.
Whatever remains, however improbable, must be the truth.
Right.
Exactly. Constraint grammar starts by assigning every possible tag to a word. So can is a noun and a verb and a modal. It assumes everything is true. Then it uses these strict handwritten linguistic rules to delete the impossible ones.
Like, if the word before this was the, then delete the verb tag.
Right. It just whittles the sculpture down until only the correct tag remains.
Yeah.
And the proponents of this system, like the NCG, tag or claimed accuracies of up to 99%.
99%. That beats the neural network.
It does. Now, there is some academic beef here. The source notes that the way they calculated that 99% is debated, mostly around how they counted ambiguous words. But the point still stands. Clear, human-written logic is sometimes more powerful than a black box neural net.
And then there's the hybrid hero, Brill's tagger. This one feels the most like how a human actually learns.
Eric Brill's approach was brilliant, yeah. It starts with a dumb guess. It just assigns the most frequent tag to every single word. If race is usually a noun, it tags every race as a noun.
Which means it gets a lot of stuff wrong, initially.
A lot of stuff wrong. But then the system compares its dumb guesses to a correct answer key, and it looks for patterns in its own mistakes. It learns patches.
So it realizes, hey, every time I tagged race as a noun, but the word right before it was to, I was wrong. It should have been a verb.
Precisely. So it writes a rule. Change noun to verb if, the previous tag is to, and it just stacks these rules, hundreds of them, one after another.
It's self-correction.
It is. And the best part, once it learns all the rules, you don't need the heavy AI anymore. You can compile those rules into what's called a finite state transducer.
Which is just a fancy way of saying a very fast checklist.
A very fast checklist. Brill's tagger can run 10 times faster than those complex hidden Markov models because it's just running down a list of learned patches.
So we have these incredible neural networks reading backwards and forwards. We have Sherlock Holmes' reductionist grammar, and we have these self-correcting rule learners. But, and here is where we hit the wall.
The ceiling.
Yeah. The source mentions that despite all this technology, we seem to be stuck. Whether it's 97% or 97.5%, we just aren't hitting 100.
And we really need to ask, does that 3% gap actually matter?
It sounds like an A+. If I got 97% on a test, I'd be thrilled.
In school, yes. But in language processing, the source makes a really sobering statistical point. If you have 97% accuracy, that means you have a 3% error rate per word.
Okay, let's play that out.
In a sentence of, say, 20 or 30 words, the probability of the whole sentence being completely correct drops significantly. If every word is a roll of the dice, eventually you're going to roll a failure.
The math says almost every third sentence would have at least one tagging error.
Exactly. And if you are using this tagging for something downstream like Google Translate or extracting medical data from a patient report, one single error can completely flip the meaning.
If the computer thinks leaves is a verb when it's actually a noun, your translation is just garbage.
Yeah, the patient leaves the hospital versus the patient eats the leaves. Very big difference.
So that 3% error rate is actually a major barrier to perfect understanding. It's the sand in the gears of the entire machine translation industry.
But, and this is the thought I really want to leave you with, the expert in the text poses a really philosophical question about that ceiling.
That's about the humans, isn't it?
It is. We judge these machines against a gold standard, usually a text that's been tagged by human linguists. But the source notes that even expert humans disagree on the tags about 3% of the time.
Wait a minute. So if the humans disagree 3% of the time, and the machine is wrong 3% of the time,
then the machine might essentially be perfect, or at least as perfect as the vague, messy rules of language will ever allow. If the teachers can't even agree on the answer key, how can the student possibly get 100%?
That is mind-blowing. We're trying to build a machine that is more consistent than the messy creatures who invented the language in the first place.
It raises the question, is ambiguity a bug in language that we can solve with better math? Or is ambiguity a fundamental feature of human communication that will never be fully resolved?
That is a thought to chew on. Next time you type a sentence, spare a thought for the poor algorithm trying to figure out if you're canning a can.
It's doing its best.
Thanks for diving deep with us today.
A pleasure.